Good day, everyone. Let's go ahead and start our webinar today. And first of all, I'd like to thank everyone for joining. And we are really glad that you are here with us today. My name is Lisa. I'm one of the course advisors at EIT, and I'll be hosting this webinar with Dr. Mahadi. And let's start with fixing our notifications and sounds so that you would have um, as little interruption as possible during the session. So kindly go to the gear icon right beside the little purple half circle on your lower right corner of the screen, as you can see here in the picture. And please go to My Settings. Okay, and that would be the gear icon or symbol. And then go to notification settings and please uncheck all the boxes in there so that there are no notifications that will be popping up on your screen during the webinar and it won't interrupt you. Okay, so is everyone able to hear me? Sorry, just double checking. Can I get a thumbs up or yes? Thank you so much, Dominic. Thank you so much, guys. Just shout if you are having, or just send a message if you're having any issues. Okay. All right. And I hope that you are done unchecking all the boxes in your notification settings so that we can go ahead and proceed. All right. All right. So for today's webinar, we are going to have the topic of little penguin wing for application in microaerial vehicles. And this is presented by Dr. Mahadi Hassan Masid. He is one of the lecturers at EIT, and he will be telling us more about himself later on. And these are the most common questions in all of our webinars. So I'd like to address this as early as possible so that you won't, go ahead and having these questions in your mind. So for a copy of the slides or the material that we are using today, and for the video recording as well, we will be sending a copy of those or a copy of each one of these in the next 2 business days via email. So we will send it to your email. And if you don't receive it, check your junk because sometimes it goes there. And for the certificate of attendance, you might be wondering, is there a certificate of attendance? Yes, there is. All you need to do is to request for it. We will be sharing a link to request for that or a QR code later on. And please make sure that you request for the certificate because it is not automatic. If you don't request for it, then you won't be receiving a certificate. Now, next question, is the certificate for free? Yes, it is. You don't need to pay anything. Just like the webinar, the certificate is free as well. And it's only a digital certificate. There are no hard copies for it. So it will be sent to your email as a digital certificate. Okay? Now, I'd like to give you a glimpse of some fun facts about EIT or Engineering Institute of Technology. So, we are proud to say that we are dedicated to ensuring that our students would receive a world-class education and gain skills that they can immediately implement in the workforce. And we are also an engineering specialist. There are only a few engineering specialist schools in the world, and we are one of those. And We only focus on engineering courses from professional certificates, diplomas, advanced diplomas, undergraduate, graduate certificates, bachelor's and master's degree courses, and of course, a Doctor of Engineering course. We are also industry oriented, so our programs are designed by industry experts, just like Dr. Mahadi here. And we ensure that our um, students would graduate with cutting edge skills that are valued by companies and employers as well. And of course, our program content are always updated with the rapidly changing technology and industry developments in the engineering world. And we also have a world-class Australia accredited education. So aside from the Australian government, we are also accredited by Engineers Australia and other international accreditation organizations. And for Engineers Australia, we are accredited under the Sydney Sydney Accord, Dublin Accord, and also the Washington Accord. And we also have industry experienced lecturers. So aside from Dr. Mahadi here, we have a lot of other lecturers who are highly experienced engineers who are also practicing engineering while teaching at EIT. And of course, um, we make sure that our technologies are also updated and they are also state of the art for both online and on campus courses so that we can ensure that you would have the best world class experience. And our unique delivery model as well. Our programs are designed by engineers, and we don't focus on theory alone. We are um, a huge fan of having our students be exposed to as much practical activities as possible. And even if we have our online delivery model or online version of the courses, we provide certain facilities for our students to experience as near to the real life experience as possible, like our virtual laboratory, our simulation software, and our remote laboratory as well. And of course, we have our pool of expert lecturers that you can approach whenever you have any concerns with studies or a certain topic. And we also have our dedicated learning support officers for each course. And they are the go to person of our students whenever they have concerns regarding their study in general. So that's how unique EIT is. And I hope that you would take note of those. And when you study in the future, you would be considering EIT as well. All right, so let me introduce you now to Dr. Mahadi. He is one of our lecturers, and I will give him the honor to tell us more about himself and um, his background as well. Thank you.
Thank you, Lisa. Thanks for the introduction about EIT and myself. So yeah, this is Dr. Mahadi. I recently finished my PhD from RMIT University in Australia. My campus was Bandura in Melbourne, and I did my BSc and MSc back in Bangladesh. And I was in teaching for like around, now it's been around 10 years now. And even when I was in undergraduate level, I started my research. And so far I published 3 full books with Springer and 15 book chapters at with different publisher. And also like around 10 of the book chapters is pending for publication. Those are under review or in press. And I have also published around 35 journal and a bunch of conference paper as well. And I always like to include myself in research, so I always do reviewing for the journals and conference papers and also the books. So yeah, that's the introduction of myself. Now let's jump into the slides. So the topic that I'll discuss today is there was a couple of objective in my PhD. I'll just discuss one of them for the whole presentation. So Lisa took a little bit extra time, so most probably I will not be able to finish within 5. So if it's not, please allow me a couple of more minutes. If I can't, I'll try to speed it up. But yeah, if I can't, then just allow me a couple of extra minutes. So yeah, in Melbourne, there is a very special place which is known as Phillip Island, and if we visit there, we can see a lot of little penguin, especially during the evening when they came back after their foraging after their trip. So I did my research with the little penguin. So it was a mixed up research actually. So I did both biological stuffs, and basically it was a biomimicry. So I mimic penguin. It was the plan was to mimic the whole penguin, but it was not possible during that 4 years time of my PhD. So I just mimic the wing. I did all of my research with the wing, but I took a lot of data of real penguin dive. So regarding the real penguin dive, whatever you can see here, that is a dive of a real penguin, a single dive. So the below figure, this one where I am giving the tick mark, this is a dive of a single penguin. This is a single dive of a real penguin that I took the data using the sensor. And normally the little penguin, the maximum dive that I found for the little penguin, it was like around 41 meter, but the mean value of dive was like around 13 meter. So I took a dive that demonstrate the mean value, and the upper curve, the graph that is showing on the top, it is the acceleration of the penguin. So what happened, so if we can see in that curve, so that phase of the dive, the beginning phase, so that phase of the dive which I mark with the yellow is known as descending. And at the beginning they have to overcome a lot of buoyancy force, because at the beginning the buoyancy force is lot, so they have to beat their flipper a lot, so which can be demonstrated from that curve. The acceleration is very high, but at the end, when this phase where my curve is where my mouse is right now, so this phase is basically the ascending phase, and in the ascending phase they use the buoyancy force and they do not need to beat their flipper. So we can see there from this part of the curve, the acceleration is almost zero, and they do not need to beat their flipper. They just utilize the buoyancy and they come back to the top of the surface of water. So there is basically what I mean to say. The first phase in the descending, this is the flapping mode, and the next phase in the ascending phase, this is the static mode of the flipper. So I had to deal with both of them. So the flapping mode is in the first phase, and the static mode is in the next phase. Even when it dives, it doesn't always dive. Even when it swim, if I took another dive here, so there is a phase when he doesn't dive, he only swim on the top surface, on the top surface of the water. Even on that time, the wings acts as a static mode wing. So during the flapping mode and during the static mode, so how can we say that yes, penguins swimming efficiently, or even in the static mode when they do not beat their flipper, is it a efficient thing, or can we mimic it for the application in microaerial vehicle? Either it could be static microaerial vehicle, or it could be flapping microaerial vehicle, or it could be kind of drone rotating microaerial vehicle. It could be anything, but for everything we need to do some research. That's what I did. So the first thing that I did for the flapping mode, to estimate the stroll number, so I estimate the stroll number. So if I see stroll number, is nothing but just frequency, amplitude, and velocity. So I had the velocity data, I had the frequency data, and I had the amplitude for everything. So I calculate the stall number, and there is a range. If the stall number for any flapping body is between 0.2 to 0.4, then we can say that yes, that penguin is swimming efficiently. And for the static mode, that's what was my target. For the static mode, I did like both numerical stuffs, and I validate my result with the wind tunnel data. So I will show how I did the numerical data in next part of my slides. So yeah, and there are some basic characteristics of the little of a penguin wing. It could be any penguin. There are different type of penguin, but as a little penguin is available in Australia, so I did my research with the little penguin wing. So they have like they only use their we use their flipper, that flipper for the swimming and diving and everything. They don't use their tail like the other animal, other other mammals or anything. So they only use their flippers. So that is one of the basic criteria and basic characteristic. And one more basic characteristic was they have like their span and wing area is considerably lower, as considerably lower compared to their whole body. That reduces the added mass effect, and that also simultaneously reduce the drag force. The added mass effect and drag force is interconnected with one another. So I don't want to go in detail of that added mass and drag force, but yeah, so that they have a aerofoil shape like wing. Therefore we were planning to mimic it and want to see that yes, compared to the NACA wing, which is already established, how our flipper performed, how our penguin flipper performed. So that was the target. And in currently whatever autonomous underwater vehicle is there, everything is powered by the propeller. But with the propeller, there is the problem of cavitation, and also they are not ecologically friendly, and they have a lot of wake generated behind the autonomous underwater vehicle, and they don't have better efficiency. So in order to solve all the issues, researchers are now more focusing on the flapping wing. So far, whatever research has done and whatever performance has been like evaluated, everything was done with the NACA wing. Nothing was done so far regarding the penguin wing. So if you can see there, I just mentioned so far whatever research already investigated foil, you can see all of them are NACA foil or normal rectangular foil or teardrop or elliptical shape. Those are the shapes. And if you look at the air and number of paper regarding the flapping foil, with time it is increasing. It is increasing significantly. In 2020, in 2020, the number of paper is like published paper is 25, and around every year. So researchers are more focusing on flapping foil. Either it could be implemented in unmanned water vehicle, or it could be implemented in autonomous underwater vehicle or unmanned aerial vehicle. It could be implemented anywhere. So if I go there, so the part that this part is regarding the water vehicle, autonomous underwater vehicle. So this figure is for autonomous underwater vehicle, and the other part is unmanned aerial vehicle. So the next figure is regarding the unmanned aerial vehicle. So what we can see from this figure, that uh, unmanned aerial vehicle for unmanned aerial vehicle, different researcher is try to mimic different thing, like the humpback whale wing. They have a sinusoidal leading edge in front of their wing, in the leading edge of their wing. So people are mimicking the humpback whale. This is known as leading edge protuberances. Also, researchers are focusing on inward dimple. They are developing dimple on top of the wing, or square cavity, or something like that, outward dimple. And when they did that, if you see the result here, the B means baseline aerofoil, the normal aerofoil, and M means modified aerofoil. After the modification, after the implementation of leading edge protuberances. So the stall angle in case of baseline aerofoil is 12 degree and modified aerofoil is 16 degree. Just to let everyone know, I don't think everyone is used to the stall angle. Everyone know the term stall angle. So if you put the angle of attack here, and if you put the coefficient of lift here, so the target of aerofoil is to develop lift. So if you increase the angle of attack, the coefficient of lift increases, but after certain point it suddenly decreases. So that point when the coefficient of lift is started to decrease is known as the stall angle. So with the leading edge protuberances compared to the baseline aerofoil, the modified aerofoil is is increasing the stall angle. That means in baseline aerofoil, if you consider this one, this figure is for baseline aerofoil. In case of the modified aerofoil, it could be something like that. After that point, then it will decrease. So it increases the stall angle. That is a very good result. So whatever biomimicry has done so far regarding the unmanned aerial vehicle is just done with the leading edge protuberances by mimicking the humpback whale, or kind of with the leading edge protuberances by mimicking the humpback whale, or kind of with the dimple surface, just with the surface of the upper surface of the wing. Nothing has done so far regarding the penguin wing. So that was another motivation for us to do the research regarding the penguin wing. So yeah, and that is another research gap. If you look into this figure, so the Boeing 747, that is the plane where we travel, everyone, either Boeing or Airbus, and that is Cessna. That Cessna is the like practice, the pilot normally practice with that Cessna, and then large bird, and then micro aerial vehicle. So then insect. So how we can differentiate all of them? The Boeing 747 normally runs between 10 to the power 7 or 10 to the power 8, that range of Reynolds number. And the Cessna runs between 10 to the power 6 to 10 to the power 7, large bird 10 to the power 5 to 10 to the power 6, and MAVs run between this range, 10 to the power 4 to 10 to the power 5. But what is the issue? If you can see that smooth conventional, that blue curve signifies the NACA aerofoil, the conventional baseline aerofoil that I just mentioned here, that first line, conventional baseline aerofoil. So in case of NACA aerofoil, when the Reynolds number is high, it is providing better result. But when the Reynolds number is decreased, you can see the sharp decrement of the result here. At the range of 10 to the power 4 to 10 to the power 5, at which MAVs run, the microaerial vehicle, the performance, the efficiency, which is also known as the ratio of coefficient of lift and coefficient of drag, is reduced significantly. So that was another reason we have to look into something so that we can solve that issue, that at the lower range, when the Reynolds number is lower, 10 to the power 4 and 10 to the power 5, we should find something when the ratio of CL and CD should be higher. So that was another research gap, because of which we look into the penguin wing. And that is again jump into this part, the flapping mode. The flapping mode, at the beginning I said penguin both shows flap and static mode. So this is the this figure is for the flapping mode. So I did say the stroll number should be in the range of 0.2 and 0.4. if we found the stroll number between this range, then we can say that yes, the flapping mode is efficient. So for penguin, the red dots are for penguin. For all the 7 penguin, I did try it with the all the 7 penguin data, which are most conventional. Little penguin, emperor penguin, king penguin. There are 7 actually. There are more than 7 actually, but I use 7 penguin data, and I found for all the penguin, it is showing the result between 0.4, 0.2 to 0.4. That signifies yes, the flapping mode is efficient. And for the static mode, I'll show how I did it. Is it efficient or not? Is it perform aerodynamically better compared to the NACA aerofoil or not? I'll show. So yeah, that was the first step. I bring the penguin. It was a carcass. It was not a real penguin because it is impossible to like scan a real penguin. So I bring this little penguin from Phillip Island. My supervisor arranged it for me. One of the scientists from Phillip Island, he gave it to us for a couple of months. Then we scan it, and the scan version, the scanner give the STL file to us. So when I get the STL file, I have to use two software, Geomagic DesignX and Autodesk Mesh Mixture, then finally SolidWorks. After using that 3 software, it took me like around 2 months to convert this scan version to that penguin. So then I finally found this penguin, which is known as nerve surface. And SolidWorks and all the design software, either simulation software, everyone can read only the nerve surface. No one can read the STL version. No software can read the STL version. So I did it like this way. So after getting the penguin wing, then I just chop it. When I get the nerves version, then I chop it. Then I use the 3D printer and printed the wing. So this is the printed wing that I printed with a 3D printer. And here are the basic parameter, like the wing span was 0.24 and mean chord. So I don't have this is the chord length. So these are the chord. I don't have a specific chord, unlike the aerofoil. Aerofoil has a fixed chord, but I don't have a fixed chord. I have different chord length at different places. So I had to take the chord length in every 0.1 millimeter. Then I took the mean value, and this is the mean chord. And while doing simulation, I'll show a demonstration of simulation within 10-15 minutes. I need to put the value of mean chord because during generating the domain, we need the mean chord. And this is the area that I simply calculated, simply just multiply wing span with the mean chord and found it. And those are the properties of air. And this is the 3 cases. This is the 3 cases of air velocity. Because of that, the generated Reynolds number was in the range of 10 to the power 4 to 10 to the power 5, which is the range for MAVs, micro aerial vehicle. So the target was to perform the numerical simulation and validate the result of numerical simulation with the wind tunnel data in the range of MAVs. So from where we get the range, where we get the Reynolds number, so that was the figure from where we get the Reynolds number. So this is the range, 10 to the power 4 to 10 to the power 5. So we did our simulation in this range. So we randomly selected these 3, 5 into 10 to the power 4, 7.5, and 1 into 10 to the power 5. That's the maximum range, and that's the medium, and that is close to maximum. So here is the domain that I generated for my penguin wing, and this is the mesh that I generated for the simulation. And the number of elements for that generated mesh was quite high, but for the simulation that I will demonstrate today, I just scale it down so that we can do it very quickly. I already did it. I already opened it as well. So regarding the meshing, the target was I use body of interest, excluding the face meshing and edge meshing and inflation layer, I use body of interest. What is body of interest? If we can see in this figure, this particular figure, so our wing is here. So we are more interested close to our wing. We are not that much interested at the upper surface or in the bottom surface. We are more interested close to our wing. So therefore we make the mesh finer here, then a little bit coarser there, and very coarse at that place. And when you create any domain, so as I just said, we need the chord length C. So when you define your Reynolds number, so that is the Reynolds number, rho VL divided by mu. So rho and mu are the properties of air, V is the velocity, and L is the length, characteristic length. As a mechanical engineer, all of us know that what is Reynolds number. So L is the length. So in case of aerofoil, what length, or maybe in case of penguin, what length should we put? So that is the length, the chord length we should put. The chord length we should put to estimate the Reynolds number. So that is how we calculated the Reynolds number. And while developing that domain, let's say that is our 2D domain, and this is our aerofoil. Sorry for that bad drawing. So here, how can we do that? How can we give the dimension? So from that point to that point, from the leading edge to the inlet, the domain should be 10 times to the inlet. The domain should be 10 times of the characteristic length. What is characteristic length? That is the characteristic length. And in case of aerofoil, that is the chord length. And this one should be 20 into characteristic length, and from the upper surface to the wall it should be also 10 into L, and this one also should be 10 into L. So those things are written nowhere. I'm just telling it from my experience. So that's how I did it. 30C, C means chord length, this one is 10C and 20C. So 20C is the height. So 10 and 10. So that's how I generated that. And when you generate the mesh, how can you know that yes, your mesh is good? So there is two characteristics by which you can check your mesh. The first one is skewness. You have to check your skewness. For skewness, there are different value: acceptable, bad, unacceptable, bad, acceptable, good, very good, and excellent. So for my case, I found 0.92, which was in the acceptable range. So that's all right. And orthogonal quality of the generated mesh, it is good when it is close to 1. So I found it close to 1. So yeah, my generated mesh was good. And also there are studies regarding the mesh sensitivity analysis. That means with the change in mesh, so I generated this mesh. So anyone can say what will happen if you increase the number of elements, if you make it more finer, if you make it more finer here, or maybe make it more coarser here, what will happen? So that could be a question. If you change the number of elements, if you change the mesh, will your result change? So for checking that, you have to check that mesh sensitivity analysis. So that's what I did here. So when the number of elements was 1.4 into 10 to the power 6, my value was 3.5. When I change it, it decreased to 1.5. When I change it more, it decreased to 1. But when I change it more and more, it is not changing anymore. I got a straight line. So after that point, the result is not changing anymore. So there is no meaning you are increasing your number of element more and more, and because it will take your computational time and cost. So I selected that point. So whenever you publish any paper, or whenever you do any simulation anywhere for any study, any engineering or anywhere, not only engineering, you have to do that mesh sensitivity analysis. Either you did it in ANSYS or COMSOL or any other software. So that's what you need to do. And the final thing is the wall y plus, that also you need to check. That depends on the model that you will use. If there are different model k epsilon, then k omega, and there are also a more powerful model that took more computational time. So different model demands different y plus. If I go deep into the y plus, it will take more time. So just as a thumb rule, for k omega model, we need a y plus over the aerofoil surface or over any surface that we are studying. It should be less than 1. That is the thumb rule that you need to do. So that is all about the mesh and 2-point correlation. When you do like master's thesis or PhD thesis, so regarding your mesh, you have to check, or uh, regarding your study, you have to check that 2-point correlation or Kolmogorov -5/3 law. So this is the two thing that you need to calculate. So the spectral density, it should have a -5/3 curve, the -5/3 curve. That is the one thing. And the slope of the curve should be -5/3. And for 2-point correlation, there is a calculation procedure for 2-point correlation. If your domain is good and if your result is good, if your mesh is providing better result, all of your 15 point behind your wing, let's say that is the domain and that is the wing, and the wake will generate here. If you took 15 point behind your inside your wake, like 1 point, 2 point, 3 point, kind of like this, then at every point the calculated 2-point relationship should be over 0.2. So we did it, and for every case we found over 0.2. So now let me jump into the simulation first, then I will talk about rest of the thing. So just give me a sec. So I already did that, just to save time, I already did that. Let me do one more time. So this is the interface for ANSYS workbench that I used. So there are three software which is already installed inside the workbench. So you can use any of them. I used to like the new design modeler geometry. So just click on that. And it takes a little bit of time to open it up. Yeah. Then select the XY plane or any plane you like. So I always select XY plane, and just to reduce the computational time and just a second. Yeah. So I think, yeah, the screen is showing. So that's the interface for the design modeler. So I already created the geometry. So for the created geometry, you have to just import the external geometry. I put it here. I use SolidWorks to create my geometry, and the geometry was created in the format of IGES. If you use the design modeler, we have to use the IGES format. So this is the IGS format. I just import it, then hit generate. So I generate it, and then I need to give the domain. So when you want to create the domain, go to that same plane, XY plane, and hit sketching and create rectangle. So that domain could be created either as a C mesh or as a rectangle, up to you. So both of them work fine. So then I have to do the dimensioning. Let me do it very quickly. So that dimension, although I need to give 10 into the 10 into chord length, but just to save time, let me do it just 5 times. And this one, let me do it 1 time. And we can use the constraint to make symmetry that both line, because this one and this one should be. So I want symmetry with respect to this line, and this one and this one. These two should be symmetry, and I have to put the dimension for these two as well. So vertical dimension, these two, just make it 0.3 for now, and it automatically take the other one. So when we have that, just create and extrude it. So we have to select that sketch one and hit apply and add material. Make sure to select add frozen so that your this domain doesn't impact the aerofoil. Then hit generate. If it is generated, okay, so I have to change this extrude length and then hit generate. Again, it is very high, 0.03. Yeah, so that is generated. So the next part would be create more domain inside that domain, because I want to put the body of interest. So in order to do so, just sketch one more rectangle, just doing it randomly. Make sure to use the constraint with respect to this axis, this one and this one. All right, and then create extrude and this surface, apply and add material, again frozen and 0.05. That's it. And do one more time. So go to XY plane and new sketch, sketching rectangle. So do it one more time. And then go to extrude again. Select your this sketch, apply and add frozen. Should be all right. Okay, so I have all of them. Now I need to use the Boolean function and go there and subtract. So my target body is the most bigger surface, the most bigger body, and my tool body is the aerofoil, which I selected and hit apply and hit generate. So if you see now my domain is generated. So why I did like this way, because I want to implement body of interest while doing the simulation. So just go there and hit update, then go to meshing and edit. Okay, so it is here. So now for meshing, as I am saying that I will use body of interest. So for that you have to click the sizing. You have to click the sizing, then hit the outer body. So for selecting body, we have to select this one and then outer body, and then here element size is selected. So instead of element size, write body of influence. Just select the body of influence, then which one you want to select. So just hide the upper body, then we have this one, then go to there again, select this middle one, and we have to put some element size value. So just let randomly put 0.013, and then again show this body and hide this one. Do one more time. The sizing, select this one, hit apply, then body of influence again, and then hide the outside body again, then go to body sizing 2, then select this one and hit apply, and 0.006. Okay, so I need the outside one now and I don't need the inside one now. So okay, all right, now let's do a couple of more sizing. So the next should be face sizing, and for face sizing, make sure to select the face from here and hit Control and select both faces and hit apply, and the face sizing is 0.0035. I'm just randomly putting the values. Okay, and one more sizing. Now we will do S sizing of the aerofoil. So for the S sizing of the aerofoil, of the wing actually, let's do all of them, and this one. All right, hit apply and then put a value of 0.0015. One last thing, as I will use k omega model and I want a y plus value of less than 1, so we have to put inflation layer. So select that inflation and select that outside body, and what should be the boundary. So the boundary should be the wing, that we generated. Sorry, the boundary should be the wing. So we have to select the inner face, the both inner faces. Is it selected? No. So we select both the inner faces and hit apply. Then we have to insert the first layer thickness here. When you select the first layer thickness, then how can we calculate the first layer thickness? That will generate a y plus 1. So for that, you have to go there, compute grid spacing for given y plus. So I want to simulate at a Reynolds number of 2 into 10 to the power 5. So for that, my speed is 29.22 and my length of the chord length of the wing is 0.1, and I want a y plus value of 1. So if I give everything, if I give the velocity and rho mu is already been here, and if I put the value of L equal to 0.1 and y plus equal to 1, then if we just hit compute, then we'll found the delta S value and the Reynolds number. The Reynolds number is 2 into 10 to the power 5, and we have to just copy this delta S value from here and then go back to the meshing, and first layer thickness, the delta S value, you have to just put it here. And it is there is a kind of thumb rule. The maximum layer we have to put 15 and growth rate 1.2. So if that is the case, then if you hit generate, the mesh will generate it. I already generated the mesh, so I'm just showing you. Just give me a sec. Yeah, so that's the mesh that I generated. Then I give the name outlet. This is my outlet. These are my walls everywhere. This is my inlet, and this is my aerofoil. So I generated the mesh and I give the name for everything. Then in the next step, I have to update the mesh. Then I have to go to setup. So let me open the setup. So if you go to the setup, so let's do it steady. We can do it transient. It's a bit more complicated, but for a real life experience, we have to do transient. Then model, from here you can select the model. There are different model. As we are planning to use the k omega, so here is the k omega model. Just select this one. I already selected this. Then close it. As we are not dealing with temperature, there is only one physics, which is fluid flow. We don't need to turn on the energy here. So that's all right. Then for material, make sure the material is air, and the properties that you are using here, rho equal to 1.225 and mu equal to that much. It is similar, the value is similar here, 1.225 and 78. If not, then just change it. You can just insert the value and change and close it. Then the velocity, the inlet boundary condition. Here the inlet boundary condition, I use 29.22. I just insert it and hit apply. So when this one is done, then go to reference value, and here for reference value always compute from inlet, and the area you have to calculate chord into the chord value into the span value, multiplication of chord into span. This is close to 99% correct. That is the area. You have to select this area. Normally it is 1 here. If you don't change it, you will not get correct result. Then the next step is to go to the method section, and regarding the method section and solution method, there is a big book of Pope from USA. He has said that for which kind of simulation, what method you need to use. But as a thumb rule, if you don't want to spend that much time, just use everything second order upwind, and the scheme should be coupled. So after that, go to the report definition, and you can create the report that which if you double click here and hit here, then if you go to force, the drag force and lift force, you can simply create them. So I already created both of them, the lift and drag. Then go to monitor. So for monitor, 10 to the power minus 6, the absolute criteria, absolute convergence criteria, 10 to the power minus 6 is a thumb rule. We can always use that. If it is not like this way, just change it to this way. Then if we are done up to there, then we have to initialize the data. Just click initialize, hybrid initialization, then run calculation. So I already did run the calculation, and this is my drag data, drag coefficient data, and this is my lift coefficient data. The value are 0.82 and 0.067. As this version of ANSYS, which is installed in my computer, is a student version, it does have a limit. It does have a limit of number of element. If we go there in the mesh, and at bottom the statistics, the number of element is 427k. For student version, the number of element, the limit is 512k. So if you increase that, you can do the mesh sensitivity analysis. And regarding the quality check, you need to just simply click here in the quality, and then the mesh metric. Here you can simply just click the mesh metric skewness and found the value. The skewness value, the maximum value is 0.94, which is in the acceptable range. And also the orthogonal quality, if we click that, we can simply find the orthogonal quality 0.99, which is also in the acceptable. So both of them are correct. So finally, when we are done with everything, so as we define it and found the result, so just go to the report definition, lift, and hit compute. So if you hit compute, you'll get the coefficient of lift here, 0.82. So two last thing here regarding simulation. If you go to XY plot, let's have a look into pressure coefficient. So go to XY plot and isosurface. Isosurface means let me create isosurface. So just go there on isosurface, in result, in create isosurface. We want to create an isosurface over the aerofoil. Let's name it ISO 2, and we want to do on Z axis at the middle in the in compared to the span. In regards to the span, it should be in the middle. So just create that, the ISO 2, then XY plot. So pressure coefficient, just click pressure coefficient and ISO 2 and save and plot. So you see, we get a pressure coefficient figure, something like that. And if we go to the website and see already published data regarding pressure coefficient, we found a similar figure like that. And also from here, if you want to look into the Y plus value, just go there again, and instead of pressure, select turbulence and go there and select Y plus and save and plot it. Excluding at the beginning, at most of the places, the Y plus value is less than 1. 98% places, the Y plus value is less than 0.1. So that's how you need to do the simulation. Very simple way. So let me jump into the slide again and finish it up in 2-3 minutes. Just a sec. Oh, sorry. I'll take the question a little bit later. I'm almost done. So that's how I did the simulation, and that is the wind tunnel that I use for validation of my result. So these are the result for the experimental and numerical one. So for NACA wing, the stall angle happens at 10 degree here. But in case of penguin wing, we found that the stall angle is at 15 degree, which is one of the major issue regarding the aerofoil performance. We move the stall angle at a Reynolds number of range 10 to the power 4 to 10 to the power 5. So that was a very that was a promising result. And finally, this is the validation that we did, and I just said regarding the stall angle, and this is the figure. Like for NACA, the stall is at 10 degree, and for the penguin wing, which is in yellow, this is in we found it in 15 degree, and this result is already been published in one of the good journal of Springer. And also one of the book chapter is published from here. And if you can see from this figure, at 10 degree and then 15 degree, at 10 degree and 15 degree, there is no separation. Separation just started, but a little bit. But in case of 15 degree, in case of 20 degree, for penguin wing, the separation has been started. And yeah, these are the pressure contour and coefficient of pressure. And if we see this figure, we compare our result with the NACA wing. So compared to the NACA wing, this is the difference. So this is the thing because of which the lift force is generated compared to the difference in negative higher pressure and positive lower pressure. In case of penguin wing, the difference is quite high for every angle of attack. For every angle of attack compared to the NACA aerofoil, the penguin wing is showing more promising result. So that's how we did it, and this is the these are the summary of all the results. So yeah, that's all from my side. I did a bit faster at the end. I didn't explain the result here, but finally we found that even at the end, I'll see the question. Just give me one more minute. So at the end, we also see the effect of scaling. We see the result for effect of Reynolds number. That was one thing, and also we see the effect of scaling. We scaled down the wing and we scaled up the wing. And see the result that with scaling how much the result is changing. So for scaling, we change the aspect ratio, we change the chord length, we change the span length, everything. So by changing everything, we found a kind of similar result, maybe 5% change in result compared to when scaled down on scaled up wing compared to the scaled up and scaled down wing. We found pretty much similar result. So yeah, that's all from my side. So let me have a look in the question. So Lisa, should I read the question and answer, or they should ask me?
Hi, Dr. Mahadi. Yes, if you have questions, you can go ahead and ask
Okay.
Dr. Mahadi
Yeah.
about it.
Yeah.
And after the question session, I will be featuring some courses, and then I will be sharing the link to the certificate as well. So maybe we can have a few more questions if you are okay with it.
Okay. So the first question, may I know the name of the software? Yes, the name of the software was ANSYS Workbench. The one that I showed today, this is the student version. It is free for everyone. If you just Google it, you can easily download and install it. That is very easy. And okay, another webinar target are solely for teaching us how to use this software. Yes, that's up to you guys, Lisa. They requested for another webinar for teaching that. Thank you so much, Vin.
Okay. Okay. Sorry. Go ahead.
Yeah. Yeah, I think no more question. I can't found no more question.
All right. So I am now
Yeah,
sharing the link to the
yeah. One last
certificate
question.
chat.
Uma asked, Lisa, sorry for interruption. Uma, so the simulation that I did, it was for a static wing, not for a flapping or heaving wing. So there is nothing about the motion. So we had to only deal with the velocity of the air. So I didn't do any simulation regarding the flapping wing. So I only have the result for the flapping wing, the experimental one, but for the simulation one, it was for the static wing. No, the aeroplane wing is very big wing, so we have to deal with the scaling it up, because the aeroplane runs at a Reynolds number of 10 to the power 7 to 10 to the power 8 range. But whatever result I show today, it is only in the range of 10 to the power 4 to 10 to the power 5. This is for microaerial vehicle, and microaerial vehicle is used by the military forces for the reconnaissance and for this kind of stuffs, like kind of drone. For drone you can use that wing, which runs in the range of 10 to the power 4 to 10 to the power 5. Yeah, no. Thank you. Thank you, Coin. Yeah, Lisa, I think I'm done. There is no more question left. You can continue.
Thank you so much, Dr. Mahadi. That was um, a really informative session, and I'm sure that a lot of our attendees here had learned so much about your topic today. And yep, let me just go ahead and continue on here. So I'd like to let everyone know that we have a range of courses in mechanical engineering. So we have our advanced diploma of mechanical engineering technology that will start on the 16th of October. And we also have our graduate diploma of engineering mechanical that will start in January. We also have graduate certificate in mechanical engineering. So that's a 6-month course. The graduate diploma is a 12-month course. We also have online Master of Engineering Mechanical starting in January, and a professional certificate of competency in mechanical engineering. And in February, we have our undergraduate certificate in engineering foundations, undergraduate certificate in mechanical engineering, and our online Bachelor of Science in Mechanical Engineering too. We also have the professional certificate of competency in vibration analysis, balancing alignment, predictive and precision maintenance of machinery. That will also be in February. And if you want to know more of our courses, you can just simply go to www.eit.edu.au and just go to study areas, and you can choose mechanical engineering as well. And then for those who asked about the upcoming webinars, you can go to our events page. That's www.eit.edu.au/news-events. So those are our upcoming events and webinars. And we have the introduction to power distribution and low voltage design, electrical design process that are upcoming. And for those who would like to request for the certificate of attendance, I had sent the link in our chat, and I'm sending it now as well. You can also use the QR code in here to scan and request for your certificate of attendance. Okay. So since the question and answer portion is already done, I would like to um, share to you our contact information. Again, the website is www.eit.edu.au, and our head office is in Wellington Street, West Perth, in Perth, Western Australia. We also have our phone numbers here. If you're from inside, if you're from Australia, then you can use the 1300 number. If you're from outside of the country or outside Australia, you can use the +61 number. And if you have concerns or questions regarding webinars, just send us an email to webinars@eit.edu.au. Also, our courses are in here, www.eit.edu.au/schedule, and you can see the schedule of the upcoming intake starting next month up until the next year. And again, I am going to post our certificate link in the chat so that everyone can still see it. And to those, excuse me, and to those who have questions regarding Dr. Mahadi's topic today, you can still send an email to webinars@eit.edu.au, and we will forward those questions to Dr. Mahadi, and we will be sending a reply to those questions to you for those who still want to ask more clarification. All right, so I am going to put this back on the QR code page so that everyone can finish requesting for their certificate. Please note that we have a deadline in requesting for certificates, and that would be on Sunday, end of day Sunday. So we hope to have all those requests as soon as possible so that we can process it and be able to send it to you by next week. Okay? All right, I'll be posting this QR code for a few minutes, and I will be posting the link again so that everyone can access it. So thank you so much for your participation today. We are glad that you have attended this webinar, and we look forward for you to also attend our upcoming webinars in the future. Just visit our events page, and we highly appreciate everyone's efforts in here. Thank you. Have a great day.